All right, this is APBC Calculus. We are doing Unit 9, Section 9, the last section in the unit. This is a BC only topic. We are finding the area of the region bounded by two polar curves. So let's go ahead and jump in. So recall that we know the area inside a single polar curve, right? The area is 1/2 the integral from alpha to beta of r of theta squared d theta. So if we want the area between two polar curves, that is the area inside one curve and outside the other, then we basically find the area inside each of the curves and subtract the larger area minus the smaller area, like the larger outer area minus the smaller inner one. So if I wanted this like sort of purpley pink section, I would find the area inside the blue curve, the bigger curve, from alpha to beta, and I'd find the area inside the smaller curve, the pink curve, from alpha to beta, and I'd subtract them, right? So blue area minus red area gives me this purple shaded region. Well, that means that we can get a formula that basically says we're doing the area formula we already learned for the blue, the big curve, right? So if I go back for a sec, the area for the big curve, right here, minus the area for the little curve, or if we combine them into a single integral, it's 1/2 the integral from alpha to beta of big R squared, the big radius, the outer radius, minus the little r squared, which is something that hopefully sounds a little bit familiar to you from when we did the disk method when we were talking about functions in Unit 8. So cool. All right, so let's go ahead and set up but not integrate an integral expression. So we're going to do a calculator and non-calculator part of this. So we're going to set up an integral expression to find the area inside the blue curve and outside the red curve. And then we're going to use our calculator to actually find that. But we're going to do the part where we, without a calculator, set it up, okay? So the first thing I need to do is I need to figure out these bounds, right? So the first thing I have to do is I need to find bounds. And I'm going to do that without a calculator because I was told that the first part of this is non-calculator. So I need to know when the two radii are equal, right? So I need when 3 plus 2 sine of theta equals 2. That's when 2 sine of theta is a 1, or when sine of theta, oh, sorry, is a -1, my bad, subtracting is hard, is a -1/2. Well, this is negative pi over 6. I recognize it's also 11 pi over 6, but the issue here is that I need to consecutively integrate from here to here, and I can't do that if it's 11 pi over 6. So I know that it's also 11 pi over 6, but I need to integrate forwards, right? So if I did 7 pi over 6 to 11 pi over 6, I'd be doing this window, and I don't want this window. I don't want, so it is not this window down here. So I can't do 7 pi over 6 and 11 pi over 6. I need to start at negative pi over 6 and go to 7 pi over 6, all right? So the part I'm going to do by hand is what I want is 1/2. The little red one is the r is 2, right? So 1/2 the integral of big R. So the big R, sorry, there's a 2 there. Right, it's the 1/2, the big R, so 3 plus 2 sine of theta squared, minus the little r squared, and I would definitely just leave that as a 2 squared with respect to theta, and I'm integrating from negative pi over 6 to 7 pi over 6. So this is my integral expression for the area. This is the stuff that I have to do by hand myself. Like I have to get this, I have to find the bounds. Then I'm just going to type in my calculator, right? So since I'm already in polar mode, I'm just going to lead into it. You don't have to be in polar mode. We've seen in other videos that it's absolutely fine to be in function mode, and in some cases actually preferable to be in function mode. So I'm going to go ahead and call this my R1, and I'm going to call 2 my R2. You might think that's overkill. You might think I should just use the 2. That's your business. It's up to you. So I'm going to go ahead and do 0.5, right? Math 9 to function integrate, right? And then I want vars over to y vars, and I want polar. So I want R1 squared minus, and again, if you just want to do 2 squared, that's fine because it's a 2 in this case. If you want to do R sub 2, that's fine. With respect to theta, right, from negative pi over 6 to 7 pi over 6. And this is really where, again, if you didn't have, now I understand that obviously you have a calculator here because I let you do the second half with the calculator, but it's very possible you could have this first half of the problem without a calculator. And if you can't find the bounds, you're going to have a problem. So I end up getting that this is a 24.187, right? And that's the part that I make my calculator do. So I do all the other stuff, and then my calculator just types numbers. I still have to know how to put stuff in my calculator, obviously. All right, so now we're using the same windows, right? Now we're using the same one, except on this one, I want the other half. Well, now I want this window. Well, this is the window from 7 pi over 6 to 11 pi over 6. And I did make both of these, so these are the same functions, right? I was kind of lazy. I actually, combination of laziness and also wanting you to see the difference about if I integrate a different chunk. So not only is this a different window, but now the red is the one on the outside, right? The red is the outer curve. So my area is going to be 1/2 the integral from 7 pi over 6 to 11 pi over 6 of the 2 squared, because the red is the outside curve now, and then the 3 plus 2 sine of theta quantity squared with respect to theta. Please don't clean that up at all, right? So this is stuff that you are going to do, and then your calculator is going to do the extra work for you, right? So now, honestly, I'm just going to hit second enter, and I'm going to switch which functions where, right? I'm going to make this a second insert 2 squared minus, I'm going to delete that. So that's my 2 squared minus r1 squared with respect to theta. And then this time I'm going from 7 pi over 6 to 11 pi over 6. And then we'll double check everything's legit. And it is. So I get that this is a 2.195 or 6. And that's it. All right. Yep. Cool. All right. So calculator problem. Write an integral expression for the total area between the given curves. You can use your calculator to find the area. Okay, so it's okay to graph these. It's not a bad idea, especially because most of us are not great at graphing in polar. So when you're graphing them, it is definitely worth being in polar. What you're going to find, so 3 sine of 5 theta, right? If you graph these, and we'll zoom standard in just a sec. So I'm going to zoom 6, so we'll zoom standard and polar. Now that's pretty tiny, so let's zoom in. There you go. So what this is this is essentially a curve that has, it's like a flower with 5 petals, right? The smaller, like, so this is the inside curve, because if you look, the biggest this will ever get is 2. So essentially you have a flower that looks kind of like this, and I'm not going to pretend I'm good at drawing it, but you have a flower that looks like this. Let's not judge me too much. Okay, and that's this one. That's the outer curve. And then inside it you have these smaller petals that all seem to be sort of contained, right? So the area that you're trying to find, right, so that's this guy. The area that you're trying to find is this area in between, and they shouldn't overlap. As you can see, they're better on the diagram. Actually, I could be a smarter human and just screenshot this and give you a better picture. Hey, look how much better that is than anything I could draw. So the area we're trying to find is this area between the petals, right? So the area between the big petal and the little petal, right? So I kind of need to find the bounds, right? That's going to be the first logical thing that I would need to do. So in order to find the bounds, there are a couple options, right? But honestly, I think the easiest option is to just set 3 sine of 5 theta equal to 2 sine of 5 theta. You're going to get sine of 5 theta equals 0 when you subtract it over. And so you're asking yourself, hey, where is sine equal to 0? Well, it's at all the pi's, right? So 5 theta is going to be plus or minus 0, and pi, and 2 pi, and 3 pi, and all the pi's, blah, 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 right? So you're going to get that plus or minus 0, pi over 5, 2 pi over 5, 3 pi over 5, etc., right? So basically, you need one of these. You can find one of these bounds, right? So one of these, like, you can pick one, right? So this is from pi over 5 to 2 pi over 5, right? It's the first window. And actually, I lied. That's from 0 to pi over 5. My bad, because here we go. There's 0, and there's pi over 5. So I can use the first window, right? And then once I know what one of them are, I can just multiply by 5, right? There are 5 of them. So for one of these petals, I could say that the area is 1/2 the integral from 0 to pi over 5 of big R squared, so 3 sine of 5 theta squared minus little r squared, which is 2 sine of 5 theta squared with respect to theta, right? So again, let me do a slightly better job of writing that. So the area is 1/2. So it's the area of one petal is 1/2 the integral from 0 to pi over 5. Sorry, again, just a little bit sloppy up there. right? So that's one petal, but I wanted all the petals, right? So we wanted all the petals. If I wanted all 5, I'm just going to multiply by 5. So it's going to be 5 halves times that integral. And that's basically the deal. I could have also just found one of them in my calculator and multiplied my answer by 5. That would also be totally fine. And then I'm going to use the calculator to actually find the area, right? So that's the part that's me, right? And then I'm going to use the calculator to get an approximate value. So I used R2 is the bigger one, so I'm going to quit out of this, right? So if I hit second, enter. So you can either find it as a half and then multiply by 5, right? Which is fine, right? Which I guess I'll do because oh, here we go. Second, insert 2, or you can make it a 2.5 for the 5 halves at the front. In this case, my R2 was the big one, so I'm going to go to var over to yvar's polar and pick R2 squared minus R1 squared from 0 to pi over 5. And then we should be good. So I get that value, and then, so that's all of them because I did the 2.5, so that's a 3.926 or 927, depending on if you round or truncate. All right, let's do a couple more. All right, so we're going to go ahead and do the same concept, but with P2. All right, let's go ahead and do a P2 similar to E2. So here we have 2 polar curves. I've already taken the luxury of putting them in the calculator. So if we graph these, because it's a calculator section, what we can see is that we have a rose curve that's inside of a circle. And it doesn't look circular because we're not zoomed square and your calculator window is a rectangle. But you can see that if I did zoom square, you'd see that this is a circle. And we'll just drag this over here for a sec and make it a little bit bigger. So the area that we're talking about finding, right, the area between these, is this area outside of the rose curve but inside of the circle, right? So that's the area that we're talking about. So the easiest way to do this, because we are looking at this full circle the whole way around, the easiest way to do this is to, we know that to get the entire circle, we'd need the full 2 pi. And the same is actually going to be true of the rose curve. To get the entire graph of the rose curve, you'll need the full 2 pi. And you can sort of see that if you toy around with your calculator a little bit. If you don't make the window a full 2 pi, if you make your theta value only go to pi, you'll see you only get half the curve. So so you can kind of toy with that if you're ever in a spot on a calculator section where you're not sure if you need the full 2 pi. In order to get that entire curve here, you do need the full 2 pi. So so the easiest way to do this is just to say that the area is going to be 1/2 the integral of the outside curve, which is the circle, so 4 squared, minus the inside curve, which is a 4 cosine of 2 theta quantity squared, d theta, right? You have to do that work, and then your calculator does the rest. So if I quit out of this, 0.5, I do math 9, right? Now this is, I called this my R2, and I called, 2, and this my R1. Honestly, you really don't have to use R2 for 4. You might just want to use 4, right? So you could just do 4 squared minus, and then when you go to vars over to yvars, you want polar, and you want R1 squared, comma, with respect to theta from 0 to 2 pi. The other way to do this that's a little bit harder is to try and do each section of it, like to do one section and then recognize that there are 4 sections, but it's a lot easier here to just do the full circle. And you get that this is a 25.132. And that's it. All right, so moving on. All right, so sometimes there are 2 curves, but the area we want actually isn't the area between the 2 curves, so that's what we're looking at here. So you have to be really careful at what area you're looking for. So this is a non-calculator because we're setting up but not integrating an expression for the area of this shaded blue region, okay? So what I want you to notice is that this area is actually 2 different things happening, right? In this half, right, so from here to here, this is just a half circle, right? That's a half circle. So I can actually find the area of that part. So I'm just going to call that part number 1. I can find the area of part number 1, right? This area right here, this half circle, by just saying, hey, that's 1/2 pi r squared because that's a circle. So that's just a pi over 2, right? And I can do that without writing an integral if I want, right? But to find the other chunk, right, to find the rest, well, this piece, right, this piece and this piece, those are going to require that I integrate inside a polar curve. So I could have written this as an integral, right? I could have, if I wanted to write this, this blue piece, right, if I wanted to write this blue piece as an integral from negative pi over 2 to pi over 2, because remember, it does have to be a consecutive window like this, right? I could have written this as a 1/2 r squared with respect to theta from negative pi over 2 to pi over 2. That's fine, but honestly, in that situation, you'll see a lot of times that you're just going to have the AP give the answer to that section because it's something that's just geometric. Now for this section, right, this section's a little bit different, right? So this section is the window from pi over 2 to 3 pi over 2, right? Because 3 pi over 2 and negative pi over 2 are at the same spot, right? But that's the area inside this other curve. So to find this area that I'm going to call this together 2, like both of these, right? To find area 2, I'm going to need to do 1/2 the integral from pi over 2 to 3 pi over 2 of that r squared. So one way you'll see this, right? One way you'll see this is that my answer could be written, right? My answer could be written as the two separate integrals. So area 1, which was the integral from negative pi over 2 to pi over 2 of, I can put the 1/2 in front if I want, 1 squared d theta, right? Plus the area of the thing I called number 2, which is the integral from pi over 2 to 3 pi over 2 of 1 plus cosine theta quantity squared d theta, right? So that's one way you might see that answer, right? So area 1 plus area 2, and that's the whole thing, right? But again, to be honest, since this chunk is a geometric shape, right? Since this is a geometric shape, it's very likely that you would also see this just as the answer to what this geometric shape is, which is the pi over 2 that I explained right here, because it's a half circle, plus the integral expression for the other half. So either of those would be fine. In either case, you did set up an integral expression to find the area. It just happens that one of the areas is a convenient geometric shape in this one. So, so the other way you might see the answer is with that value just calculated ahead of time. So you might see it as this whole thing. And that's kind of the idea. So that's a trick question because notice it's not between the two curves, right? The area between the two curves would be this area here, right? Because this is outside the red and inside the blue, or it would be this area here that I didn't ask for because it's outside the blue curve but inside the red, right? And that's not the section that I was asked for. So the same situation here, right? In this situation, if we look up to this point here, right? So basically this like Pac-Man shape, right? I did a kind of bad job of drawing that one, but you'll get, oh, my bad. Let's fix it this way. So this Pac-Man shape, right? The Pac-Man shape is just a part of a circle, right? So the Pac-Man, right? So I'm gonna call this area 1. It's kind of like Pac-Man's eye, right? Area 1, the Pac-Man, is a sector of a circle. So you could actually find that with geometry, right? This is a geometry formula. So we really need to find out what these two angles are. And you can find it out pretty quickly. Now on this one, I didn't actually do the work to set them equal to find the angles because it was pretty clear by visual inspection that they were pi over 2 and this either 3 pi over 2 or negative pi over 2 because they were on the axis. I could have found that by setting r equal to r, and I would have gotten 1 plus cosine of theta equals 1. So I would be asking when is cosine theta equals 0, and sure enough, it would be at all the pi over 2's, right? So plus or minus pi over 2, 3 pi over 2, etc. And those are the values I got. Here, it's not quite as obvious by visual inspection, so I should probably find the bounds, right? So I should really find what those two angles are. So I'd set 2 minus 2 cosine theta equals 1. So negative 2 cosine theta is a negative 1. So cosine theta is a half, right? And so that means that this angle is pi over 2. Sorry, pi over 3, rather, my bad. And this angle, depending on how you're looking at it, is either negative pi over 3 if you're looking at it in this consecutive window, or it's 5 pi over 3 if you were looking at it going this way around the circle, right? So there are two ways to do this, okay? Option number 1. So option 1, which doesn't pay any attention to geometry at all, is to recognize that from negative pi over 3 to pi over 3, so this window on the right-hand side, right, this chunk right here, I just want the area inside the blue curve. Well, the blue curve is the 2 minus 2 cosine theta, so 1/2 2 minus 2 cosine theta quantity squared with respect to theta, right? So that's this area, these two little ones. So we'll just call these guys together area 2, right? So that's area 2, right? Plus, and then area 1 is the integral from pi over 3 to 5 pi over 3 because, again, I have to use consecutive values of theta. They have to go in order, right? And so I can't go backwards. I can't use negative pi over 3. So pi over 3 to 5 pi over 3 of the other thing, which was a 1 squared with respect to theta, right? So that's fine. That's a great answer. That would give you the area. That's okay. But the other way that you might see it on the AP is on an AP, especially if this were multiple choice, right? The other option you might see is this same first integral, right? Because that piece is not a nice convenient geometric shape, right? So you'd still have to write 2 cosine theta quantity squared d theta, right? But this piece is a sector of a circle, so you can find this using geometry, right? You can actually find this area using geometry. So let's go back up for a second, look at what this is, right? So from pi over 3 to 5 pi over 3, right? That would be 4 pi over 3 radians, right? Because it would be 5 pi over 3 minus pi over 3. So that's how many radians it is. So if we want to know what percentage of the circle, this is the part of the circle, right? This is the sector, right? And this is the full circle, right? A full circle would be 2 pi. So if you wanted to clean this up a little bit, what would end up happening is you would end up getting that this is a 4 pi over 3 times a 1 over 2 pi. So you'd be able to cancel the pi's, you'd be able to cancel a 2, and you'd get that this is 2/3 of a circle. Well, that means that your area, since we now know that this is in fact 2/3 of a circle, then the area would be 2/3 pi r squared. And so the other way you might see this formula is with this integral that you never bothered to evaluate, right? But instead of using the integral for the second expression, you'd see this as a 2 pi over 3 because, again, this was something that you could get with geometry, right? So just want to throw that out there. Those are the two options. Notice that the big trick here is that I'm not inside one curve and outside of the other. These are two separate parts. And hence the involving one or more integrals. So you might see this with 2 integrals, or you might see it with 1 integral and a value you can find with geometry. And that's it for this video, and that's it for Unit 9.